Okay, so we've talked a little bit about what the individual level responses are to competition, that often individuals will grow more tissues in order to be taller than neighbors, to have more roots than neighbors, and potentially to have more leaves shading their neighbors. Now I want to talk about the population level responses or sort of factors of competition. And generally, ecologists imagine that there are resources and there are consumers. Right? So most populations interact primarily through the consumption of resources. So two plants might compete for the same source of nitrogen as a resource. At the same time, right, herbivores are consumers and plants are resources for herbivores, right? So a plant can be a consumer and a resource depending on what we're looking at. And the reason this matters is because we're trying to get to communities. That communities can be considered to be many populations tied together in a web of these consumer-resource relationships. So first of all, we need to think about what is a resource. And your textbook actually talks about this, and your textbook defines resources as any substance or factor that leads to increased population growth rate when its availability is increased in the environment, right? And so you could imagine that these experiments are straightforward to do, that the resources for plants are things like light and water, nutrients like nitrogen, phosphorus, potassium, and also potentially space, right? You could imagine that you could move rocks around to create or remove space or something like that for stems. One thing your textbook doesn't talk about, though, is that resources can be either substitutable or essential. So your textbook talks about essential resources, but it doesn't talk about substitutable resources. And ecologists make a distinction between the two. So essential resources are what your textbook says they are. They're required for growth, and you can't replace them with anything else, right? So light, nitrogen, phosphorus, right? If I shade a plant, I can't just give it more phosphorus and as a substitute for light. It doesn't work that way. Light is light, and you can't replace it with anything. Substitutable resources, on the other hand, are what they sound like. They are resources that can be replaced with another kind of resource. And the best way to think about this is that lots of resources are available in multiple chemical forms. So nitrogen, for example, can be often taken as nitrate or ammonium. It turns out that plant roots can take up about 20 different amino acids, right? So there's 26 or 28 different kinds of nitrogen, and each one can be substituted for the other. And it's not the case that they're perfectly substitutable, right? Like you could imagine that if you're trying to obtain your calories in a day, chocolate is substitutable with like a salad, but they're not one-to-one substitutable in terms of the calories that they have. And it's the same with things like nitrate and ammonium. So just to review, the populations have certain features, right? Remember, the carrying capacity is often thought to be set by the environment and often thought to be related to resources. And as the density of the population approaches the carrying capacity, then its growth rate drops to zero. So let's think through how competition might affect some of this growth, right? So consider a plant population growing according to the logistic equation, which we've already seen. There should be a bracket here. I don't expect you to memorize this. I'm going to continue to remind you of that. But I do expect you to be able to work with it if I gave it to you. Right, so the idea is if we want to predict the population size n, or density n, in the future, so at time t plus 1 time step in the future, we need to know the current population size and put that in a few different places. And we need to know the intrinsic rate of increase, r. That's the growth rate in the absence of any interactions. And we need to know the carrying capacity. And if we knew all that, we could probably make a graph. You guys know how to do that. Okay, well now let's imagine a second plant population, and I'm just going to pick P because it's near N in the alphabet and it's related to plants. And it's the same equation, right? But it's got potentially a different rate of increase, a different carrying capacity that may depend on how it uses resources. And if we knew all that, we could probably make that graph as well. And so then the question becomes, how do we add the negative effect of these two populations competing? And I think sometimes people can't imagine how math people come up with these equations, but we already know that we need to have a negative effect of competition, so we're probably going to need a minus sign. And this term here in both equations, this sort of population size divided by the carrying capacity, that's what actually adds the negative regulation of growth. And so it turns out that we can just add the negative regulation of both populations on one population. So as this population grows, it limits itself. So it'll slow down as it approaches the carrying capacity, but the other population will slow it down too. And we just have to have some kind of like competition coefficient. A just describes how much this population reduces the growth of this population. And then we need another term, B, to describe the opposite. And when we plot them together, now we can get different responses. So Here's some output where I use the numbers that we've been using all along. So we start with 2 individuals in each population. I set A and B, these competition coefficients, equal to 0.5. We're going to use our favorite value 100 for no reason other than it's simple, and we'll keep R at 0.25. So species don't have to have the same intrinsic rate of increase or the same carrying capacity, but it's simpler if they do. And so if we were in a room together, I would ask you, what do you notice that's different about these populations? In fact, let's stop the video here and we'll do a survey. So what do you notice that's odd about these graphs compared to what you know about what these should look like with these parameter values? So answer that survey and we'll pick this up on the other side.